Hello, in this video, we are going to add to our list of series convergence tests as we go through this chapter. So far, we've looked at geometric series and telescoping series tests, and we're going to add to that list today divergence test, integral test, and p-series test. So let's go ahead and start with the divergence test. Now, if you're looking around online or in other textbooks, you might see this referred to as the nth term test. Whichever one you see, we're talking about the same thing. I'm calling it the divergence test. And the way this test works is you take the nth term of your series and you take the limit as n approaches infinity to see what you get. If the limit is equal to something other than zero, then the series diverges. So it could be anything from the limit equals 1 to infinity or does not exist. If I get anything other than 0, then I can say the series diverges. And if you're wondering, well, why in the world would this be the case? Well, think about what a series is. It is a sequence of partial sums. And so each new term in the sequence is another sum where I'm just taking the previous term and adding something onto the end. And if that something that I'm adding onto the end is getting tinier and tinier, it's approaching 0, then the sum is going to approach a particular value. And because you're just adding something that's practically 0 as you get closer and closer to, as you go to infinity. So this is really a requirement of a series to converge, is that the terms, the nth term, it has to be approaching 0. Now, the thing to be careful about with this test is that if the limit does equal 0, that does not necessarily mean the series converges. It's a requirement for convergence, but I can still have a divergent series where the limit approaches 0. So if you get 0, the test is inconclusive, and you want to go back to the list of other tests and try a different one. This only works if the limit happens to not be equal to 0. Okay, so let's give this a try. So I want to use the divergence test here to determine whether the series converges or diverges. And remember, the only result I can get from using this test is diverges. So what I'm going to do is set up that limit as n approaches infinity of the nth term, which is that 1.9 to the nth power. And then I evaluate the limit, and I hope that I get something other than 0 here. Now, looking at this, because the base is a value greater than 1 and n is approaching infinity, this whole term is going to approach infinity. If I had gotten something less than 1, so maybe it was 0.9 instead of 1.9, then this limit would have approached 0. But as is, it is equal to infinity, which is not 0. So that means that I can conclude that this series diverges by the divergence test. And it's really important to have everything I've got written here on your paper to justify your conclusion. Okay, you got to have the conclusion. You've got to state the test that you're using, so it's clear which test and which requirements you're checking. And then you want that limit, the result of the limit, and the fact that you got something other than 0. Right, and really that's all there is to it. You get all those boxes checked, and we've proven that the series diverges. The next convergence test we want to look at is the integral test. And as far as like what my go-to tests are, divergence test, that was pretty fast. Integral test is quite a bit longer, but it does apply to a lot of situations. So it's a nice one, but it is kind of a last resort for me because it takes a lot more work than a lot of the other tests that we will look at. But it is a very useful one. So how this test works is I'm going to take the nth term of my sequence and I'm going to treat it like it's a function. And even though it's not actually a function, I'm going to treat it like a function. And when I write it as a function, in order to use this test, that function has to be continuous, positive, and decreasing. Now, I'm not going to require that you prove all those things, but you do want to verify it and at least convince yourself that all those things are true before you use this test. So if there are negative terms, or it's an increasing or function, this test cannot be used. Okay, so just make sure that those things are actually true before you move forward with this test. And it's a good idea just to state it on your solution that, in fact, this is what f of x is, and it is continuous, positive, and decreasing. So once I've established those qualifiers, what I do is I'm going to set up an infinite or an improper integral here. I'm using the values from the summation notation here. So the index starts at 1 and goes to infinity, so my integral will start at 1 and go to infinity. If the series started at 5, then my integral would start at 5 as well. And then the f of x is really just this nth term. And to run this test, I'm going to actually evaluate this improper integral. So we got to remember back to the previous units where we talked about improper integrals and evaluate this. Remember, there is a limit involved in evaluating an infinite improper integral. And then whatever behavior this improper integral has, the series will have as well. So if I evaluate this and I get a real number, then the integral converges, and then also the series. If I get something like infinity or does not exist, then the integral diverges, and so does the series. So that's how it works. So let's do an example. So we're being told to use the integral test. Really, remember this criteria. It should be positive, decreasing, and continuous. And it has to be something that I can integrate. If I have something there that I really don't know how to integrate, then the integral test is not the test to use here. Okay, so we start out, I'm going to take my nth term, write it as an f of x, and then just check for myself. Is it continuous? We're going from 1 to infinity. There's no discontinuity there. Positive, I am going to only get positive values here. And if I check this is a decreasing function. The bottom is getting bigger much faster than the top, so it's going to be decreasing. Okay, so I set up my integral, my improper integral here. And then remember how we handle the infinite upper limit there by taking the limit as some new variable approaches infinity, and then we put that new variable in place of our infinity. And now that we've taken care of that infinity, we've gotten that non-real number out of the limits, I can go ahead and evaluate this integral. And this is one that can be evaluated using a u substitution. So I'm going to make the denominator my u, which means that du is going to be 2x, or 1/2 du equals x dx. And luckily I have that x in the numerator that is going to allow this substitution to work out. So replacing everything, I add in a 1/2 du in place of the x dx, and then the x squared plus 1 gets replaced with u. I can integrate this now. The integral of 1 over u is the natural log of the absolute value of u. And then I want to reverse the u substitution. So I plug that x squared plus 1 back in. You'll notice I dropped the absolute value at this point because x squared plus 1 is always positive. So I don't have to have the absolute value there anymore if I don't want. And now I can evaluate this integral at the limits of integration. So plug in b and plug in 1 and subtract. So I'm going to end up with 1/2 natural log of b squared plus 1 minus, and then 1/2 natural log of 2 if I plug in the 1 to this term. So I've taken care of the integral. The only thing left is to evaluate the limit as b approaches infinity. The last term there is a constant, so that one isn't really affected by the limit. So it really just comes down to the b squared plus 1. If I look at the natural log of something that's approaching infinity, I get infinity for that. So the last term didn't really have any consequence here. That first term is going to infinity, so the whole thing is going to go to infinity. And this means that the integral diverges because I did not get a real number. And thus, by the integral test, the series also diverges. Okay, so I've hit all the major points here, solved my integral, come up with my conclusion, and stated the tests that I used. And that is how the integral test works. So you can see it's kind of a longer test, but it does work out in a variety of situations. Okay, last test for today, the p-series test. Now, the integral test might be the longest one we do. This is one of the shortest ones, which is great. First, we got to talk about what a p-series is. So a p-series is specifically one of this form where I have a 1, really any constant will be okay here, over n to the p. And notice that n is the number that's changing. That's my index. The p is going to be the same number each time. So it might be p is squared. So it's 1 plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared. So the base is the one that's changing. Okay, so make sure not to get this one confused with a geometric series, where that one, the exponent is the one that's changing as opposed to the base here. Okay, they're kind of reverses of each other. So if I have this specifically and that into the p has to be in the denominator, so you might see it as a negative p value written at the top, which means the same thing, then I know I'm dealing with a p series. And so a p series is going to converge if the exponent there, that constant exponent, is greater than 1, and diverge if it's less than or equal to 1. So if I have some kind of fraction here as the exponent that's unchanging with each term, then it would diverge. Now, when p equals exactly 1, so I would end up with just 1 over n at that point, that's a very special case we refer to as a harmonic series, and that one's a divergent, as we can see from the p series. But that's one of those where you can get away with, whenever you see a harmonic series, you can just say, oh, well, it's a harmonic series and those always diverge. So end of story there. So it's kind of a shortcut, which is nice when we start getting to tests in the next unit where you're comparing a given series to a known series. Okay, so last example for us to do together is, and there's my example of a harmonic series. That's what it looks like. So let's do an example with p series before we end the unit here. So here is an example of a p series. I've got a constant on top and then n to the 4th power. So the exponent is the constant here. And so once you identify this as a p series, it's pretty quick to write out the conclusion. So I want to say that this is a p series. I want to identify what p is, which p is 4 here. And then I want to compare that to 1 to kind of back up my claim of whether it converges or diverges. So this is a p series where p equals 4, which is greater than 1. And whenever they're greater than 1, the series converges. Okay, so these are the things I really want to see. I want to see p identified and compared to 1, your conclusion, and the fact that this is a p series or p series test. I'll be looking for somewhere in there. And that's really all there is to it with this one. So that's a nice quick one. Okay, so we just learned 3 new tests really quick. Here are 3 examples for you to try out, one for each of these convergence tests that we just went over. So give these a try on your own.